All right, everybody, welcome back. And here we go with our retrosynthetic analysis from winter 2018, test 3, part 4. When you see this question, take note of the useful reaction. It may not be this one. In fact, it most likely won't be this one, but it will be a reaction that replaces an OH with a Cl. I want to remind you, a Cl is a good leaving group, can be used for synthesis to make bonds to this carbon. An OH is a terrible leaving group. It cannot be used for synthesis to attach anything to this carbon. We need to be able to attach something to the carbon that has an alcohol. So we must convert it to an alkyl chloride in this case. Alkyl halide of some variety, probably on your test. Then we have to realize in the first version of this question, the one with the number Roman numeral 1, we will either have an aldehyde or a ketone. That is a promise. In this case, it is an aldehyde. So we will have to remember when we do our forward synthesis that we're going to take a terminal alkyne at the end and react it with hydroboration and oxidation to make an aldehyde, because that's the reaction we learned that made aldehydes. If this was a ketone with a methyl group attached, then the last step we do over here is going to be an oxymercuration and protonolysis step. So keeping that in mind, the last step here is the first unstep here, the first backward step. Or remember, this arrow means I know how to make this molecule from whatever you draw here. You better know a reaction that makes what you're drawing here into this. And the only reaction we learned to make aldehydes was this one. There's the 2 carbons from acetylene. That corresponds to these 2 carbons, and everything else comes from the other molecule. 3, 4, 5, 6. So 3, 4, 5, 6. And we better have a halogen on here. And if you choose your own halogen, remember that had to be acetylide. Wait, I'm 2 steps ahead of myself. Crazy. Sorry. This came from here. There, H here. The last step makes a terminal alkyne into an aldehyde. I was already thinking about how to make this bond. I am sorry, I got way ahead of myself. So, do you see how everything here is the same as the molecule above? Except these 2 carbons used to be these 2 carbons, and a terminal alkyne can be made into an aldehyde, and you'll show the teacher down here. Okay, now this is the point where we have to properly draw a retrosynthesis arrow. Don't invent your own retrosynthesis arrow. I'll put mine in pink. It's a blocked arrow. It's not a reaction arrow. So if you put a reaction arrow there, I'm going to have to say something and I'm going to have to deduct something. It means I know how to make what I draw down here from here. And this is where we're at the synthesis stage. I know how to make this bond by using a nucleophile electrophile combination. And please remember, the nucleophile has to be an acetylide or an acetylide with a carbon group up here. But right now, we don't have a carbon group up there, so we don't need a carbon group here. This has to be a carbon with a halogen on it that gets kicked off by this. And you have to remember one more thing. So the halogen you should choose is chlorine. There's no magic in that statement. You better have a chlorine because you're forced to go back to an alcohol from this. And don't put an H there. Don't put an H there. Why do I have to put an H there? Why is it not writing? There's all these good questions. There. Why is the H there? It doesn't look much like an H. There. This reaction involves a backside attack on the carbon with the halogen. So whatever the stereocenter is here will be flipped here. And that's just something we have to know. It's a fact of that reaction called an SN2 reaction. It flips stereocenters. In the video, it says stereocenter is inverted. That means whatever it was, in this case, it used to be S. 1, 2, 3 is wrong, therefore it's S. And now it's R. Watch, 1, 2, 3 is right because 4 is on a dash. Okay, and now these things are not on this list. Do we have a saturated alcohol of 5 carbons or less in these things? No. Do we have acetylene in these things? No. You can't stop here. You can't stop until you end with acetylene, which is used to make acetylide. So you can draw this, acetylene. There you go. Circle it if you want. It's optional. That's on the list, acetylene. And where does this thing come from? It comes from an alcohol. So if you didn't read the useful reaction info very carefully, you might draw this alcohol by mistake. This is not going to get you full credit. It says, if the OH is on a stereocenter, then the stereocenter will be inverted in this reaction as well. So going from here to here inverts the stereocenter, and you didn't show that. You showed it being kept. So that is methyl, and this is the H here. So it flips here, and then it flips again here. So you're back to the original, aren't you? And over here, you're going to show me the forward synthesis, starting with this. So you take your acetylene and make it into your acetylide. Please choose one of the 4 appropriate bases that we started one of our lecture segments with. I think it was the first segment 2 lecture days ago, maybe last. The days are starting to run into each other. KH is a nice base to do that. Now you're going to use the useful reaction to convert a carbon with an OH to a carbon with a halogen. Just use the useful reaction I gave you. HO. Oops, no H there. Keep doing that. H is there. Just please go to the top of the page and carefully copy the reagents that let this happen. Cl here. There's the H now. That's this molecule right here. And copy the chemical up there, PCl5. Just dutifully copy it. And now you're at this stage where you have this molecule and this molecule. You just have to somehow show me they're going to react with each other. I know I put a parentheses last time, but I mean, you could do it this way too. You could just, hey, that molecule you made previously, put over this arrow. That means it's reacting. This is a nice way to show it too. And you're going to make this. You're going to make this. Stereocenter got flipped again. Methyl sticking out. H is on a dash. And you have this species right here that needs to be made into the target. You don't want to draw the red target symbol. Just write the word target if you want. And what chemicals will convert a terminal alkyne into an aldehyde? Answer is step 1. H. You want full credit, right? You better use the one with Saya. And step 2, H2O2 and NaOH. And that will give you the target molecule. And see if I can move these things a little so they're away from the alkyne. Yeah. There. And that is the end of that retrosynthetic analysis. I looked at my email and I didn't see any new requests. So somebody needs to speak up now, or else this is the end of today's segments. All of them will end right now. Anybody got requests? I'll check my email while you're thinking.
I have a question about the previous question that you did.
Sure. And that's this one?
Yeah, so at the top left under pKa 45,
Yeah.
where did you get that CH2?
Well, this thing is going to provide an H to this thing to make this. So remember, potassium's not an issue here. It is a spectator. This is becoming that.
Oh, okay.
And this became, oh, I don't want to write over my 25. How about a light pink? That became that, right?
Okay.
And once again, this is irrelevant. It's an anion of acetylene called acetylide. Sir, is that good?
Yes, thank you.
You're welcome. And I'm still waiting for suggestions because there's nothing in my email.
I have another question. Could
Sure.
you just quickly differentiate again between using sec-isoamyl and just hydrogen for the hydroboration reaction?
You mean the BH3?
Yeah, BH3 or
Yeah,
the
like the or H2 will make an alkene, and then that'll become an alkyne if you use the wrong catalyst. Alkene will become alkane. You might be thinking of the second retro, but let me answer your first question. You get partial credit, because you'll get some of the product that you want for BH3, 2, H2O2, OH negative. This thing has issues with alkynes, so I can't give you full credit. It doesn't give a great result. I know it'd be nice if we could use the same boron chemical in chapter 6 and 7, but the reality of it is alkynes have a slightly different reactivity than alkenes. This is the chapter 6 boron. And I mean, we could go ahead and do the other retro, and I think that would talk about your reduction question, if I can find it. Let's see, we had it on Winter 18. The second retro I can bring over real quick. It's got an alkene. Do you want me to do that?
Yeah, that would be good. Also, in the meantime, the other mechanism in which you have different chemicals for chapter 6 and 7 would be with mercury, right? It would be mercury acetate
Right.
versus mercury sulfate or SO4.
Yes, same reasons. The mercury acetate does not work well with alkynes. So we have to have a different mercury. It's still mercury 2 plus, but it's mercury 2 sulfate. So, and the acetate, it works well in 6, but not in 7. That was a reciprocal relationship. You got to have the right one with the right pi bonds. So, reminder, previous page, since it's relevant over here, we'll put it under a line here. Chapter 6, chapter 7. We had the mercury, HgO, that's a 6. OAC twice versus HgSO4. And this was a 2-step process with that and water. This was with this and water. And step 2 was sodium borohydride. And that combination gets you a alcohol. And this one, H2SO4, that combination gets you an enol, which tautomerizes to a ketone. So that's a 6-7 quick review there. That's my lame attempt at tautomerization short form, and I don't think it went over very well. Tautomerization. So when we come back from break, we're going to do, oh, you brought this up, so it's a good time to look at it right now. I think that covers the things you brought up. And after break, we're going to do this one. It's also from the, was it Winter 18? That's the same as the previous one. Yeah, Winter 18. Wow. And this time we're going to do 2 parts of synthesis. It got cut off a little bit, but you guys have the originals. There's more to that sentence, but not much. Ends with, I think, is the only thing that's missing there. Just right, ends with. Wow. Ends. Okay. And that will do after the break, and it's worth more points. And we still have the same useful reaction. I'll write that here. Same useful reaction. So the PCl5 reaction is still in play. And we'll be back after break to finish this up. Be a good stop. See you soon.